Recently, there have been efforts to make the process of recharging quadrotors autonomous. By making quadrotors being able to recharge themselves during a mission, we will save time and human effort. In order for the quadrotors to be able to perform such a task, a precision landing of the quadrotor is required. Having been motivated by this challenge, our team has proposed a new algorithm for landing on a battery charging platform. In order to approach this problem, we calculated a function based on the geometry of the workspace. The derived function is called the difference function. The difference function is an angle defined in the triangle between the opening of the charging station and the current position of the quadrotor for a given time. Because of the disturbances and uncertainties present, we assume that the direction of the desired velocity and the quadrotor's velocity are not the same. Therefore, the quadrotor's motion angle can be approximated to be within a possible range. For any given velocity vector within this range, the quadrotor is able to reach the charging station. The coordinates of the 2 points of the docking mechanism are constant. However, the current position changes over time when the quadrotor is in motion. Therefore, for any given instance of time, we can calculate an algebraic function of the angle d. Taking a closer look at how the difference angle changes, we can see that along a constant height z, as we move toward the center, the value of the angle increases. We can conclude that by moving towards the center line of the charging station, we maximize our angle. A second generalization can be made when we move downward along the z-axis. It can be shown that when we are above the docking station, we maximize the difference angle by moving downward towards the charging station. However, this is only true when theta is equal to 0. A special case would be when the quadrotor descends toward the charging station while not being aligned with the center line. To show how the difference function behaves in this case, we plotted the gradient of the d function. Taking a closer look at the gradient of the difference function, we see two lines at 45 degrees to the horizontal. Along these two lines, the derivative with respect to the height z is 0. Below this line, the derivative is negative. And above these lines, right above the charging station, the derivative is positive. Using these characteristics of the difference function, we can implement the method of gradient descent to guide the descent and landing of the quadrotor. The gradient of the difference function will update the next desired position until the quadrotor has landed. In the picture at the right, we can see the simulated parabolic trajectory. This is the desired trajectory since it avoids collision with the charging station and allows for the proper vertical rendezvous of the battery. Next, we will see a test flight of the working algorithm.
Yeah, I'm doing it.